Hey, good morning, class. Mr. Bean here. This is for AP Physics. This will be video 42 for Unit 4. We're going to be discussing work, kinetic energy, and the work energy theorem. All right, so we'll go ahead and start off with you should have this study guide here, and we'll take a look, let you go ahead and read the objectives here. And we'll go ahead and come down here to work. Now, you should already got this from the initial study guide, but if you need to review work here, there's some more reading here to help you with understanding of work. We'll go ahead and scroll down here, and we want to stop here and kind of focus on on this part right here. Okay, so what this means is what this whole thing, this whole equation here. Let me go ahead and get a red here. This is kind of like a mathematical formula for work. So work is the ability, or energy is defined as ability to do work. Okay, and what is work? Okay, so work, we'll go ahead and use W for work here. It's is force. Now, this is how it's usually presented. It's going to be presented as a vector quantity here. Force times, we're going to say here, delta x, which is displacement. Delta x, and you have two vectors interacting here. Okay, so you have two vectors, and this will be the cosine of theta is the angle between the cosine of the two angles between. Okay, so what does that actually mean? So let's suppose I have a box here. Okay, and let's say a force is being applied horizontally to this box. Okay, so here the angle theta is going to be 0. Okay, because this is the force vector here, and the displacement, or delta x, is also in this direction. So delta x and force are parallel, and the angle between them is 0. Okay, so when we do this, then we have that force, right, is a vector times delta x, right, and here we have the cosine of 0. Okay, and in degrees, the cosine of 0 is 1. So this ends up just being force uh, times delta x. Because the force and displacement are parallel, this can be considered maximum work. That can be considered. Okay, and the units here, this is Newton, this is meter. So Newton meter gives us the unit of joules, or if we're in Britain, joules. Okay, joules, but joules. Now, take a look at this one here. Now, we're at an angle now. Okay, we're at an angle. So when we do this here, we have to break this up into components. Okay, so here we have the x component right here. This is fx, and go ahead and use another, we'll use green here. And this here is, will be f sine of theta, right? F sine of theta. There we go. All right, so here, since the displacement is in this direction, okay, well, they have delta r, but we should be flexible. So here we need the parallel component of the force. Okay, the parallel component. So what that means is that work here is now going to be F. Okay, the parallel component is F cosine of theta, like so. We'll put it in parentheses, and we're going to have here times delta x. Okay, but you can see here they have r, but we'll go ahead and use delta x here. But sometimes this is rewritten as this. It's going to be the force parallel times delta x. All right, so this means the cosine. So when you see this, it means the cosine component. Okay, we want to make sure we get that squared away, and that's where this comes from here. Okay, and go ahead and read this here. And go ahead and read. Now, this is an important topic here, so I'll make sure we read this part here. Uh, force is a conservative force. Okay, so let's make sure you read this paragraph here, and we understand what conservative force means. That means that friction is not acting. So we want to make sure we read this, and units are joule. Okay. All right. So go ahead and on Edpuzzle, we'll go ahead and try to answer 5.1. We're going to hit pause and let you work on that. Okay, so now go ahead and work on 5.2. Go ahead and hit pause. All right, now on 5.3, I'll give you a hint here. So just to look at it here, so there's a ramp here, right? And you are pushing, well, you push a crate with a force of 10 newtons. Despite your pushing, the crate begins to move in this direction. Okay, so delta x is in this direction, delta x is in this direction, but the applied force is in this direction. Okay. Now, when you do ramp problems here, this theta doesn't really apply here because along the ramp, this and this are parallel along the ramp. So long as the force and displacement are parallel, this theta here doesn't necessarily apply. This only becomes a factor if the angle theta here, or if the force is applied at a different angle. But that we'll assume that's parallel along the ramp here. So notice here that this is directly opposing the force. So in this case here, theta is going to equal 180 degrees. Okay, so go ahead and use that and see what happens. All right, hit pause. Okay, 5.4, it says here, how much work is done in lifting a 8-kilogram box from the floor to a height of 2 meters above the floor? So let's take a quick look here and see what we got going on. So here's a box here. You're going to lift it in this direction. Okay, so we have delta, okay, we'll go ahead and use delta y since we're in the y direction. There's delta y, right? And it says how much work is done in lifting a 8-kilogram box from the floor to a height of 2 meters. Now we got to be careful. How much work is done? Okay. Now, okay, two things to consider. Two things. Okay, two things. Is it going to be done by you, or is it going to be against gravity? So we have to be a little bit specific here of what we're talking about. Against gravity. Okay, so if it's you, okay, so if it's you, it's simply just going, so the force in this case, if it's you, is just going to be mg, okay, because the direction delta y is in this direction, and the force is also in this direction because you are doing it. If it's against gravity, gotta be careful now, right? Delta y is still in this direction, but gravity is acting in this direction, right? So mg is in this direction, okay, against gravity. So this here, theta in this case is going to be 180 degrees, right? Which gives us a negative sign for cosine of theta. Here, theta is 0. So it's positive. So we got to be careful here. So we'll say how much work is done by you to lift this up. Okay, go ahead and give that a shot and see what we got. Okay, 5.5. Barry and Sydney pull a 30-kilogram wagon with a force of 500 newtons. There's the applied force. Here's the parallel component. Acts 30-degree angle to the horizontal. Calculate the work done. Okay, we should be able to do this right. So we want the force, the parallel component of the force times delta x. Okay, and everything here is needed, so go ahead and give that a shot. We hit pause. Okay, all right, same thing here. Work in 5.06, the work done in lifting an apple 1 meter near the Earth's surface is approximately what? Okay, so we'll go ahead and assume it's you. You are doing the work. Okay, you're not working against gravity or done by gravity, but you are doing it. Okay, we'll hit pause and let you guys work on that. Next problem here, 5.07. A child applies a constant 20 Newton force along the wagon, which makes a 25-degree angle to the horizontal. Okay. How much work does the child do in moving the wagon a horizontal distance of 4 meters? Okay. So we need the parallel component of force, and we also need delta x displacement. So go ahead and try this out and see what you get. We'll hit pause. So the next topic here is when you have we already did this in Hooke's law. So if you have force and displacement and you graph this, area under the curve is going to be the work done. Okay, so energy or the work done is this area under the curve. Now in a calculus class, this would be integration. Okay, but we'll do the non-calculus version. So luckily for us, these are nice, simple shapes. This is a square, this is a triangle, or this whole thing could be a trapezoid. But you figure out what you want to do here. And so here's an example here worked out for you. So this area, you have area of the square. Excuse me. You have the area of the triangle. So here's the rectangle, here's the triangle, there's the formulas, plug in the appropriate values, and we have work done is 35.5 joules. And just to reiterate, work is a scalar quantity. Okay, it's not uh, it's magnitude only. It's not a vector. Okay, the negative sign only comes in if you're talking about work done by you or against you or something of that nature. But we'll get into that momentarily. Okay, all right, 5.08. So go ahead and try this one here. A boy pushes pushes a wagon here, and here's force and here's distance, and go ahead and work this problem out. We'll hit pause. All right. Go ahead and 5.09, same thing here. We'll go ahead and figure out the work done when force is plotted against distance. Go ahead and try this one here out. We'll hit pause. Okay. All right. So next problem here, 5.10. This is a worked out example, and we'll go ahead and show this here. And it's talking about now we're going to be moving a box with friction. So here it says an 80 kilogram wooden box is pulled 10 meters horizontally across a wood floor at a constant velocity. Okay. So that means acceleration is 0. So keep that in mind. Constant velocity by a 250 Newton force at an angle of 37 degrees above the horizontal. If the coefficient of friction, kinetic friction, means moving, is 0.315, so mu kinetic, we are given as 0.315, okay, right here. Find the work done by friction. Work done by friction. Okay, so we have to think about that. Work done by friction. All right. So first thing is go ahead and try to draw a box here of what we got going on, right? And we want to make sure that we get the parallel component. So this is going to be so Fx, the parallel component, Fx, which is the parallel component. Let me go ahead and erase this real quick here. Okay, so Fx, the parallel component, right, is going to be 250, right, cosine of, was it 37 degrees? Cosine of 37 degrees. Okay, so we have that there, and or you can also do a free body diagram here, and that we get all the components here that you need, right? Okay, so the next step here is we're going to go ahead and write Newton's second law in the x direction here. Okay, so what we got here then is, so what does that mean? Okay, so you can see this formulation here, or I'll go ahead and do it over here. We have some of the forces, right, in the x direction. Okay, we'll start off with ma, right? Okay, but acceleration is 0, right? It is 0. Okay, so okay, so the uh, so see, it's 0 here. Okay, so some of the forces is 0. However, the only force acting in this direction is the force of see. Hold on here. Let me hit pause real quick. All right. So we have here the applied force minus the force done by friction, right? Force done by friction equals 0, like so, right? Okay. And so we have to do, okay, so the applied force, okay, so there's a applied force here, here's a force of friction, okay, and so what we need to figure out is what is this applied, or so there's this kind of a subtractive effect. We have 250 cosine of 37 degrees going this direction, and we also have a force of friction acting in the opposite direction as well. Okay, so what we can do is, so what's the work done by friction? Okay, so let's go ahead and take a quick look here and see what we got going on. Okay, so here we have the applied force here, right, equals the force of friction. All right. Now, the applied force here is going to be nothing more than 250 cosine of 37 degrees, right? 37 degrees here equals the force of friction. Okay, force of friction. Okay, so now, so if I do 250 times the cosine of 37, I should get about 200 newtons. So 200 newtons is the force of friction here, is the force of friction. Okay. All right. Now, some of you might be wondering, well, Mr. Bean, isn't the force of friction, is not supposed to be like mu kinetic mg? Because if I do force of friction kinetic, if I do 0.315 and I do it times 80, and I do it, or times 80, and I times it 9.8, well, this here is saying the force of friction is equal to, uh, was it? I got 246 here. Okay, how can this be 246 and this be 200? Well, this is assuming that, remember now, this one here, we're assuming we're pulling it horizontally. This is not being pulled horizontally, being pulled at an angle. So when you're pulled at an angle, there's an extra component in the y component here that's reducing the normal force. Therefore, it's not quite 246. So in this case, the applied force is being this way, so it was moving. So this force that we're applying of 250 cosine 37, which is 200 newtons, is sufficient to overcome friction to keep it moving at a constant rate. So that is a good, good question that does come up. All right, so finally now, so work we know is going to be, so in this case, it's going to be work done by friction, right? Work done by friction, okay? And it's going to be, here we have work done by friction, and we'll have here delta x times the cosine of theta. So work done by friction. Okay, you got to be careful now. Work done by friction. Okay, so what is the actual work done by friction? Okay, so we look at it. We have here 200 newtons. Okay, work done by friction. Okay, we have that. And delta x is going to be, what's it going to be? It's 10 meters, right? 10 meters here. Okay, and now, if it's work done by you, this would be cosine of 0. It's work done by friction. So it's 180 degrees. Work done by friction. Okay, so multiply this all out and we get negative 2,000 joules. Okay, so this is the work done by, by friction, not by you, but done by friction. So we got to be very careful of what we're talking about here. By friction. Okay. All right. So go ahead and kind of think about that for a minute. And if you need more questions, let me know. Okay. So 5.11. Okay. We have 4 carts here initially at rest on a flat surface are subjected to varying forces as the cart moves to the right, a set distance depicted in a diagram below. Rank the 4 carts from least to greatest in terms of work done by the applied force on the carts, inertia, and normal force applied by the surface to the carts. All right, we'll go ahead and pause and let you think about that. Okay, so the next section here, we're going to move to page 12. Again, here's a summary of energy. Okay, and we want to make sure that we're clear on this. Energy is ability to do work. Okay, and this is a formula here for kinetic energy. Okay, we'll be using this a lot here. So kinetic energy is just 1/2 m times the speed squared. Okay, velocity. Now, this is speed now, because if velocity is negative, like let's say like -2, or velocity is +2, let's say meters per second, we can see that squared will make it a positive. So kinetic energy is a scalar quantity. All right, so just kind of think about that. Okay, here's different forms of energy, and again, the units of energy are joule. Okay, we hit pause. Okay, so this next part here, we're almost done here. This is the work energy theorem. Okay, so I want you to definitely take some time here to read this. Okay, because this is important here. A lot of AP multiple choice questions come from this situation here. Okay, so think about when work is positive. Okay, so external work, make sure you read about external work here, how energy is increased or decreased, and so you'll make sure we have an understanding of this here. So make sure we take some time to read this. Okay, hit pause and definitely read this. Okay, all right. So after reading that, let's go ahead and take a look at 5.36. Given the following sets of velocity and net force vectors for a given object, state whether you expect the kinetic energy of the object to increase, decrease, or remain the same. So go ahead and pause, and we'll talk about this. Okay, 5.37. Go ahead and take a look at this problem here and kind of see what's going on here. We hit pause. Okay, all right. 5.38. Go ahead and take a look at this problem, and let's try to answer this one. Okay, all right. As well, take a look at 5.39. Go ahead and look at this problem and see what you think here. Okay, and all right, and here is 5.40. Last one for this discussion. Go ahead and take a look at this and read it. Okay, now if after taking this you guys feel like you have a low score, let me know. I can reset it and you can go through it again. All right. All right, that will conclude this video, and look forward to seeing you in class.